In knowledge-intensive question answering, large language models like GPT and Llama are powerful, but they're also prone to hallucinations. Why? Because their knowledge is stored in static black box parameters. They can't access real-time facts, and they often make things up when they're uncertain. This is especially dangerous in high-stakes domains like medicine, law, or finance. So researchers have turned to external knowledge sources, especially knowledge graphs or KGs. These are structured databases of entities and relationships, like Justin Bieber right arrow brother right arrow Jackson Bieber, or Greeley located in Weld County. But even with KGs, standard approaches fall short. One major method, called KG-CoT, uses chain-of-thought prompting to guide LLMs through reasoning paths in the graph. But it has two critical flaws. First, it uses a rigid hop count selector, meaning it decides how many steps to take based only on the question, not on the actual structure of the knowledge graph. For example, if the question is, who is Justin Bieber's brother? A one-hop path via the direct brother relation is enough. But if the model has to go through father right arrow son chains, it might need multiple hops. Yet the selector doesn't adapt, it just guesses. Second, even when paths are generated, the LLM doesn't know how to use them. The paths are fed in as raw text, but there's no guidance on how to interpret them. The model sees a list of entities and relations, but it doesn't understand how to reason step by step from one to the next. To fix this, a new framework called RFKG-CoT, Relation-Driven Adaptive Hop Count Selection and Few-Shot Path Guidance, has been proposed. It's built on top of KG-CoT, but with two key innovations. The first is a relation-driven hop count selector. Instead of just looking at the question, this system tracks which relations in the knowledge graph are actually activated during reasoning. It uses something called a relation activation mask, a binary vector that records which relationships were used at each reasoning step. For instance, if the model activates brother during step 1, that's a strong signal. Go one hop and stop. But if it activates father and children across multiple steps, the system knows it's dealing with an indirect chain and can dynamically adjust the path length accordingly. This is done through a step-by-step process. At each hop, the model computes relation scores based on the question context. Then it filters out inactive relations using the mask. Over time, the mask accumulates all the relevant relations used in the reasoning chain. This enriched signal, combined with the original question, is then fed into a final hop count decision layer. The second innovation is few-shot in context learning with chain-of-thought guidance. Instead of just feeding raw paths to the LLM, RFKG-CoT provides a few handcrafted examples in a structured question paths answer format. Each example includes the original question, serialized reasoning paths using the format, entity right arrow relation right arrow entity, a symbolic think template that maps path elements to logical steps, and an explicit answer format. For example, Q. What did St. Augustine do? Paths, Augustine of Hippo right arrow people person profession right arrow writer. Think, St. Augustine corresponds to Augustine of Hippo right arrow people person profession right arrow answer profession. A. He was a writer, physician, and philosopher. This teaches the model how to ground each path element and derive the answer step by step, turning raw graph data into actionable reasoning logic. Now, how well does this work? The researchers tested RFKG-CoT on 4 major benchmarks: WebQSP, CompWebQ, Simple Questions, and Web Questions, spanning single-hop, multi-hop, and open-domain tasks. The results are striking. On WebQSP, using GPT-4, RFKG-CoT achieved 91.5% accuracy, a 6.6 percentage point improvement over the previous state-of-the-art method, KG-CoT. On CompWebQ, it jumped from 62.3% to 65.1%. Even more impressive, on smaller open-source models like Llama 2.7b, the gain was 14.7 percentage points, a massive leap for models with limited parametric knowledge. Why such a big jump? Because RFKG-CoT compensates for the LLM's weaknesses. The relation mask ensures high-quality paths are selected, and the few-shot guidance ensures the model actually uses them correctly. Ablation studies confirm this synergy. When you remove just the relation mask, accuracy drops by 3.4 points on WebQSP. Remove the few-shot guidance, and you lose 2.2 points. But together, they're not just additive, they're complementary. One selects better paths, the other teaches the model how to use them. Hyperparameter analysis shows that increasing the number of candidate answer entities, K, helps, but only up to a point. Beyond 10, gains taper off. Similarly, adding more paths per entity, N, gives diminishing returns, because the top-ranked paths already carry the strongest signals. And here's a fascinating insight. The number of few-shot examples isn't linear. Too few, and the model lacks guidance. Too many, and performance drops. The sweet spot? 3 examples. More than that, and the model gets overwhelmed, what we call cognitive load. This validates the careful design behind the prompt. Beyond accuracy, RFKG-CoT offers real-world advantages. It produces interpretable reasoning traces. You can see exactly how the model arrived at its answer. It's also modular and scalable. You can update the knowledge graph without retraining the LLM. No need to pre-train or refine-tune. That makes it ideal for fast-evolving domains like biomedical research or legal databases. In conclusion, RFKG-CoT represents a significant step forward in knowledge-aware reasoning. It bridges the gap between symbolic graph reasoning and neural language models by combining dynamic relation-aware path selection with explicit few-shot guidance. It's not just about better accuracy. It's about more reliable, explainable, and adaptable AI, especially when the stakes are high. If you're building systems that need to reason with facts, whether in healthcare, law, or enterprise search, this kind of hybrid approach isn't just useful. It's essential. And that's the future. Not just bigger models, but smarter integration of structured knowledge into the reasoning process.